If you've downloaded the note frames to the Thousand Islands Borderlands crossing problem, you'll notice that in the back we have snuck in the, let me see if I can separate it, formulas that you need, because the Thousand Islands Borderlands crossing scenario problem is an MM1 problem. These are the MM1 scenarios. Anyway, you're going to see me using that formula sheet as we talk our way through this. Let's take a look. Cars traveling from Canada to the United States through the Thousand Islands border crossing must stop for U.S. Customs and Immigration. During the stop, each passenger in the car must present a passport for inspection by the U.S. Customs officer, answer questions, and declare certain valuables that may be in the car. On average, it takes a custom officer about 8 minutes, now I think this is going to be an important data point, to inspect passports and release the car for entry to the United States. Since the Thousand Islands border crossing is not heavily traveled at night, U.S. Customs and Immigration keeps only one lane open at the checkpoint plaza and one officer to process arriving cars. Between midnight and 6 a.m., a car arrives on average rate of 5 per hour. Oh, okay. Now, what's the question? Assuming this scenario meets the assumptions of the MM1 model, how busy is the custom officer during this period? Ooh, wait. You know, we should back up for a second. I was saying, we're going to need the formulas for the MM1 model, and they're included in this particular note frame if you want to look for them there. Let's look at the formulas for the MM1 model. This is the MM1 model. Oh, right. We can answer various questions about the Thousand Island border crossing as long as we have, notice that each one of these formulas requires lambda, the mean of the arrival rate, and mu, the mean of the service distribution. Okay, so in the case of the Thousand Islands, lambda would concern cars because they're what arrives at the checkpoint plaza. That's the system. Now, what is it that was said about cars? Oh, I had underlined it. Cars arrive at an average of 5 per hour. Okay, perfect. So as we answer various questions with these formulas, anywhere there's a lambda, we're going to put a 5. Now, we also need mu. Mu refers to the service system. And mu needs to speak in the same time interval as lambda, so I just went ahead and wrote per hour. Okay, the service system here is the single officer that's working between midnight and 6 a.m., right? And so we need some data on how fast that officer works. And you see it says about 8 minutes, and you're thinking, yeah, well, fine, just go ahead and put the 8. I got it. Don't put 8 here. Don't put 8 right there. What the scenario said that it takes an officer on average 8 minutes to help the folks in the car. That's very relevant, but we have to remember that when we're using the MM1 formulas, mu, the average service rate, is never a length of time. Notice this business about 8 minutes to help a car is a length of time. Mu is never a length of time. Mu is the average number of services that can be conducted in an interval. You see, an interval, what interval? Whatever interval lambda, its cousin, is talking about. Okay, well, lambda was talking about 5 cars showing up per hour. Oh, all right, this is just logic. That means that mu, the actual number that we use in the formulas, needs to tell us how many cars can be served in an hour. Well, we know that it takes 8 minutes to serve a car. So if you said 60, there's 60 minutes in an hour divided by 8, that would reveal, so to speak, how many cars could be served in an hour. Ah, right. Mu, 60 divided by 8 is 7.5. Well, that means on average the officer can serve and clear 7.5 cars per. Right, that's the number that we're going to put in these formulas. Oh, all right. Now, actually, I think we're now set to go back to the actual question, because what was the question that was asked? How busy is this particular officer between midnight and 6 a.m.? Oh, how busy? The other challenge with the MM1 model is simply recognizing which formulas tell you what about a particular situation. Busyness, how busy the server is going to be, is utilization. Notice at the top of this formula sheet, there is a formula for system utilization. That is the percent of time that the server is busy. Oh, which means that to answer that, that's all that we need here. Lambda divided by mu, system utilization. Oh, which, we need the numbers, right, that was 5 for lambda, and careful, 7.5 for mu. Well, I get that's 0.6667, or basically 67%, or 2/3 of the time. So if we were to visit this particular Customs and Immigration officer between midnight and 6 a.m. at the Thousand Islands border crossing, about 2/3 of the time they're busy with the car. About 1/3 of the time they're not. There's nobody at the checkpoint plaza. Okay, what else do we need to learn about the checkpoint plaza? What is the average wait? Okay, wait to speak to that officer. What is the probability that somebody is able to speak to the officer immediately upon arrival? Now, one thing to recognize is this is really actually two different questions. Let's work on the first one. How long on average would you have to wait to speak to this officer? Capital W for wait. Wait to speak to them. Okay, so it doesn't include the actual discussion. That is W sub Q, wait in the queue, which is, let's find it, oops, right here on the formula sheet. Average waiting time in the queue. Okay, all right. I'm just going to copy that formula over. LQ divided by lambda. You're saying, well, all right, I know that lambda is 5, right? But what's LQ? Oh, LQ is the average length of the line. It's actually another formula on that sheet. Lambda squared divided by mu minus lambda. You say, well, okay, so I'm going to need LQ before I actually solve for this WQ? And the answer is yes. One of the things about this particular statement of the MM1 model is a lot of these formulas, and you can see it there on the sheet, they kind of, they're chained together, they plug into one another. Oh, all right, so in order to calculate what we want, which is the average wait to speak to the officer, first we have to ironically calculate the average number of cars that are waiting to speak to the officer. That, we just fill out this formula. Okay, so that's 5 up at the top squared divided by 7.5 times 7.5 minus 5, right? I'm just filling out that formula. I did that work and I got that LQ was 1.33. I couldn't figure out where I'd written it down. Right? 1.333. Okay, that, interesting. So on average, there's 1 1/3 cars waiting. Yes. Now remember, this is just a means to work that. Let's take that over there. The 1.333 divided by the 5. That reveals 0.2667. All right, now, do we have an answer to the question? Or remember, it's really only actually the first question in this part. Yeah, actually, that's the answer. The 0.2667 is the answer to what is the average wait to speak to the officer. Oh, except, and this is important, what is that supposed to mean? 0.2667? 0.2667 hours. Whatever lambda and mu we're talking about, remember how ours were per hour, the result of your W formulas, you know, wait for this or wait for that, is going to be in the same units. So you're wondering on average how long you have to actually wait to speak to the officer, 0.2667 hours. That's not very intuitive. Most people don't know what 0.2667 hours is. It's very easy to translate into something else that makes like a little bit more sense. For instance, 0.2667 hours, I did this in my notes, times 60, because there's 60 minutes in an hour, reveals that, this is better sounding, that's really 16 minutes. 0.2667 times 60 equals 16. You have to wait on average 16 minutes to speak to this particular officer. All right, now that took care of this part. But there was a follow-on question. What is the probability that someone is able to speak to the officer immediately upon arrival? That's actually easier to answer, but you have to know what the link is. The probability that you'd be able to speak immediately to the officer is the probability that you would be served immediately in general, like in any system. That is the opposite of the probability that the system is busy. That is actually also explicitly a formula on the formula sheet. That is the probability of no customers in the system. The probability that you would be able to speak to the officer immediately is the probability that nobody's there at the checkpoint. When you show up, that's the probability that there's no customers in the system, which is just 1 minus lambda over mu, the opposite of the busyness. So probability of speaking immediately one minus, now in our case that's what, 5 over 7.5, 0.333333 again, yeah, basically 33%. 1 chance in 3. You show up late at night after midnight at the Thousand Islands border crossing. There's about 1 chance in 3 you'll be able to drive right up and speak to the officer. Okay, so we've answered that. Although, ironically, on average, anybody that shows up between midnight and 6 a.m. has to wait about 16 minutes to speak to the officer. Okay. On average, how many cars are present at the Thousand Islands crossing plaza during this time period? All right, that's a count. That means L. The important thing, though, is that we're looking for L sub S. How do I know that? Look at the formula sheet. There are 2 formulas that give you an average count. L sub Q is the average number of customers in the queue. L sub S is the average number of customers in the system, and it's important to be able to know when you use one versus the other. They're asking for the total amount of cars present there. That would be L sub S, which is not unrelated to L sub Q because the formula for it is L sub Q plus lambda over mu. And the good news is that for the previous problem, we had to figure out what L sub Q is so we can use our work again. Remember, we've determined that the average number of cars waiting around was 1 1/3 or 1.333. We've already done that, right? Plus, we just tack on now 5 over 7.5. Oh, and all of a sudden it's not so messy. The result is 2. So if you're hanging out at the checkpoint crossing at the Thousand Islands border crossing between midnight and 6 a.m., on average there's 2 cars there, right? There may be no cars there. There may be 1 car there with somebody speaking to the officer. There may be 2, 3, 4, 5. That will average out between midnight and 6 a.m. to 2 cars.